Okay, so our next speaker is Professor Jae-Kwang Kim from Iowa State University. So yeah, Professor Kim is an expert in survey sampling missing data. So and we are very glad that Professor Kim will visit Peking University next month. so so Jay will talk about robust estimation for missing data, which is also related to causal inference. Yeah, Jay, please go ahead. It's all yours.
Yeah, thank you for the nice introduction and the invitation. So I'm very glad to give a presentation, even though it's online. One thing I like to apologize is that it is not really causal inference topic. It's more directly related to missing data, but I hope that the idea can be directly applicable to causal inference too. So hopefully it still be helpful. So I'm going to present some recent work I did with my former PhD student, Hengpang Wang, on how to robustify estimation on the missing and random. So, okay. So here's the very basic setup where xi and delta I, yi is the observation we have, where delta I is the indicator function of the outcome response. So basically means we observe y only if delta is equal to 1. And we are interested in estimating zeta, which is the population mean of y from the observed data. So I'm going to intentionally use red color to emphasize unknown or parameter. So in particular, we are interested in incorporating omega I such that the weighted estimator is weighted average of yi can be used to estimate mean of y. So one popular approach is to use the inverse of the response probability, where we need to estimate the model parameter in the response probability model. So the basic idea is this based on the assumption that the response probability model is correctly specified and missing and random holds. Now, the covariance balancing concept is introduced. So if we have an outcome regression model in the linear outcome model with the unknown parameter beta, and then basically the error, right? So we know set hat n is unbiased for the population mean of y. So the difference has a two component. So systematic component, right? X component and the error component. And the error part, the second part, is basically mean 0. So expectation is 0 on the missing and random. So the first part is basically the bias part. But if we set constraint equation 3, so if we make equation 3 wholes, then basically the first term also disappears, right? So then this condition, so the condition equation 3 can be viewed as a constraint to the propensity weight. And you can see that when constructing the propensity weight, the motivating mode of distribution is really outcome regression model. So we didn't really use the response probability model to justify the propensity score weight. So the properties in 3 is often called the covariance balancing property. In survey sampling, this condition is called the calibration equation. So motivation is simple. The covariance balancing constraint 3 provides an unbiased estimator under the outcome regression model, regardless of the response probability model. While the weighted estimation method can be motivated by the response probability model, it may be a good idea to impose the covariance balancing condition as a constraint to find the final weight to incorporate the outcome regression model. To uniquely determine weight, we may consider minimizing certain objective function subject to the constraint 3, so the covariate balancing constraint. And for example, Muller proposed using this kind of objective function from the entropy theory. So he called this method as a entropy balancing method. But the choice of this Q function is somewhat ad hoc, and we consider an alternative approach using information projection to develop calibration properties, a propensity score weighting method. So first observation is that we can use the Bayes theorem to obtain a relationship between pi x and f0 x. So equation 4 basically says that you can express. So if f1 is known, now f1x, so fkx is the conditional distribution of the x given delta equal to k. So f1 is the distribution of among the respondent, and f0 is the distribution of among the non-respondents, right? And then this density ratio is actually a key component of the propensity score function. So if you fix f1, then function pi x is completely determined by f0. That is, there is a one-to-one relationship between f0 and pi x. If pi x is correct, then the covariate balancing property holds automatically in the population level. That is, this weight satisfies the covariance balancing already. So there's no need to add this constraint to the response probability model if it is really correct. In practice, we do not know the true response probability, and pi 0 is just the working model, working response probability model. In that case, we can conceptually, we can use the same this Bayes theorem to obtain corresponding f0 null, right? And so this is basically the baseline density for f0 derived from pi null. So in that case, because this is a working model, it does not necessarily satisfy the calibration condition, this calibration condition, covariate balancing condition. So that means we can consider imposing this calibration condition for the working model, right? So now we can use f0 null, f0 into the constraint. So the constraint, a covariate balance constraint can be equivalently written as something like this, equation 7. So basically, it's just another way of writing the calibration covariate balancing constraint. So now we have a very well-defined optimization problem. Basically, how to find omega star, minimizing a distance from omega and omega null. So omega null is basically omega null is a working model which does not necessarily satisfy the covariate balancing constraint. Because if it is true covariance balancing, then it should satisfy the covariate balancing property. But since we don't know the truth, but we only have a constraint. We only have a working model. So that means it makes sense to impose the covariate balancing constraint into the working model so that we put it as a constraint optimization problem. So basically, I like to use transform the original problem in terms of omega to the same problem in terms of f0. So then why should we use f0 instead of omega? Because if we change it to f0, then relatively it's easier to conceptualize the distance, right? Because if it's a density, we know usually the Kullback-Leibler divergence measure is a very natural measure for computing the distance between two density functions. So basically, once we transform then we can safely use Kullback-Leibler divergence measure to determine to use as an optimizer, right? The objective function. And then constraint is now written in terms of, so the constraint we want to impose is a calibration constraint or a covariate balance constraint, but we want to express it in terms of F0. So then it becomes a well-defined optimization problem. So we can actually have a closed form solution. The solution is equation 9. It's like more like a exponential family type solution. And then now once we obtain the solution, then we now transform back to the original problem of finding a pi. So it turns out that if we use this one, then if we use this one and transform back to applying this Bayes theorem, then the solution is pi star, which is a kind of augmented propensity score. So basically, we use the initial working model propensity score, but we augment by, so this is kind of the, odds, right? Odds function for non-response. And then this is a basically constraint because comes from the covariate balance constraint. So this is a graphical, illustration of the basic big picture concept. So basically, we want to find pi star, but how to do it? We transform using the Bayes theorem 4, right? So equation 4. Remember, equation 4 is this way. So we given pi, we can find F0, and so use F0 to find the use the Kullback-Leibler to find the optimization. So this line here is kind of a subspace satisfying the covariate balancing constraint. And then once you find the optimal F0 star, we transform back to pi star, which is what we want to find. So that is basically the key idea. And once you find the model, the estimation itself is relatively easy because it's actually solving parameter. Finding standard method. So step 1, we use a maximum likely estimator for the working model parameter. We use maximum likely estimator. Step 2, for estimating the augmented model parameter, we want to use this covariate calibration equation because we want to, this is what we want to impose in the sample level, right? So, so that is kind of a two-step procedure. So lambda is kind of augmented model parameter, right? And phi is more like an original working model parameter. And the final PS estimator can be simply written as something like this. And then turns out that if the true model, working PS model 11, so working model is correct, then asymptotically this guy will already satisfy the calibration covariate balancing constraint. So that means lambda hat will converge to 0, and so we'll have this estimator, original propensity score estimator from step 1, but by imposing the calibration constraint, right? By imposing calibration constraint, it guarantees that final PS estimator is unbiased under the linear outcome regression model. So basically, if the PS model is correct, then this estimator is asymptotically equivalent to the design-based. Using the because asymptotically equivalent to the initial working model estimator, which is consistent because the PS model is correct already. Okay, now if the outcome regression model is correct, then it is still also consistent because the covariant balancing property holds, right? So that means the augmented PS estimator is doubly robust. And another remark, which is the one thing I really like to deliver in today's talk, is that we can show that the augmented PS estimator, this guy, right, the left side, this guy, can be equivalently expressed as a regression imputation estimator, or something like this, where so basically, when you construct the final weight, you use some covariant balancing function, right? The function, and that implicitly implement regression imputation using the same covariate. But there's a slight subtlety, because when computing the regression weight, the weight regression is slope. The weight you use is actually comes from the propensity score weight. So this equality 15 is an algebraic identity. So it is true. You can see another way like this. So if you look at the right side of equation 5, right? The right side of equation 5, the first term is linear in y anyway, right? And yi hat is also a linear function. So end of the day, the estimator will be linear in y anyway, right? And then turns out that this estimator can be written as this one, and the relationship between these two is more like this one. So this is more like a dual expression. So the equation 15 means that the final weight do not directly use the outcome regression model for imputation, but it implements regression imputation indirectly. Okay, so we name it like a self-efficiency condition. Okay, why this is relevant? Well, this is kind of relevant to our problem, because it motivates us to develop the outlier robust propensity weight. So basically, if you look at this carefully, this guy turns out to be a minimizer of this function, right? So least square is kind of least square method, but you have a weighted least square. And the weight is basically used, has two factors, because you want to do double protection, right? So the first part is kind of developed from the response model, where the second part is to achieve the covariant balancing, which comes from the outcome regression model. So basically, this is your objective function to find a beta hat. But you can see that because this is a least square, this is not necessarily robust against outliers, right? And so maybe we can use a different objective function, something like this, and then we can even do better, right? To come up with something triply robust, in the sense that we can make it robust against outliers, in addition to being robust to doubly robust already. So that is basically the idea. Outlier robust loss function. And what is the choice of the outlier robust loss function we want to consider? Well, there's many different choices, but what we used is this gamma power divergence. So if you use this gamma power divergence, function of the squared over residual. And so if you think about that, if the residual is large, that means it is very likely to be outliers, right? And then it turns out that because gamma is positive, you are downweighting that particular unit. So we reduce the effect of the outliers through this gamma power divergence business. So that is basically the idea. So that means your final weight has actually now has three factors. One over pi I is more like a propensity score type factor. I mean the response probability model factor. A second component is an outcome regression type of factor because this guy actually achieves the covariate balancing. So as long as covariate balancing is satisfied, then under the outcome model, they are okay, right? So then now we have a third term, third factor, which is a Q factor, which basically controls the effect of the outliers. And so, and then how to choose the tuning parameter gamma is basically the idea is that you can equivalently rewrite it as imputation. So prediction problem, right? And then you can apply basically, so your predictor is a function of a gamma tuning parameter. So then you can actually apply the cross-validation idea to do optimal choice of tuning parameter. But in our simulation, the choice of gamma is not really critical. So it turns out that reasonable choice can provide good control anyway. And there's other theories, but I'm not going to cover the presentation. So in this presentation, Yumo, can you tell me how much time do I have?
5 minutes.
Okay, thank you. So I think I'm in a good, I should be able to present in 5 minutes. So for simulation setup, in the paper, I have several, other more extensive result, but here I'm only presenting some toy type simulation setup result. So suppose I have two covariate, and then first this is a very typical outcome, very typical doubly robust setup, right? So when outcome model is true and when propensity score model is true, right? And I should add one more factor where there's a outlier or not, right? So that is actually simulation 2. So simulation 2, in addition to the 2 times 2 factorial design, we intentionally create a noise. Okay, so then you can see that simulation 1 basically present the result of the without outliers, while simulation 2 shows the result with outliers, right? And so I'm not going to cover the details much, but basically OM1 is the when model is true, outcome model is true. OM2 is when outcome model is not true. And PM1 is same story. PM1 is when the response model is true. PM2 is when response model is not true, right? And then there's a tons of papers already, so it's impossible to replicate, compare all the existing methods. But at least something popular, I believe, is that Heimler method, Tan's method, and then I'm sorry I didn't include the others, but and then we compared the other methods. So many methods, but still there's a room for research that's very interesting. So yeah, well, how to let me show you directly move on to second simulation. So basically, if you we don't see a lot of gain over existing method when there's no outlier. So I'm not going to spend much time explain the result for simulation 1, but at least there's a strong some in practice outliers exist, right? So when it comes to outliers, right, then our method definitely shows a big gain. So you can see that so this is our proposed method. APS is our proposed method without considering outliers. So they are all comparable. I mean, without considering outliers, they are all comparable. Performance is really, difference is very marginal. But when it comes to, when there's outliers, our method always shows much better performance than others. So this, and then also you can see that this APS, this is the value of parameter gamma, right? Gamma is 0.3, gamma is 0.5, gamma is 1, and no real big difference. So maybe gamma equal to 1 is a reasonable choice in practice if you don't have time to do cross validation. So here's a take-home message. So information projection is applied to obtain an augmented PS model that allows for double robust estimation. Self-efficiency is introduced to obtain the equivalence between the PS estimator and the regression imputation estimator. In addition, the gamma power divergence can be used to obtain an outlier robust regression imputation estimator. It actually sacrifices unbiasedness, but it improves the efficiency a lot if there's outliers. And by imposing self-efficiency, the resulting PS estimator is also robust to outliers. So here's a summary of papers, and this is actually the paper that you can check if you are interested. Thank you very much for your attention.
Yeah, thank you. Thank you very much, Jay. Very interesting talk. Any question from the audience? So, Jay, so I want to have a clarification question first. So your final estimator is imputation estimator, right? So you use the gamma divergence
No,
to run.
I'm sorry. No, actually, that is the. So if you frame it imputation estimator, the problem is not really difficult, right? If you just think about that.
Right.
If you have an imputation estimator, then what's the big deal of using a robustified regression imputation, right? That is not really not really exciting, I'd say.
Right.
But
right.
If you view the problem as a weighting problem, right? Propensity weighting problem, and then that is not really clear how to make how to make the propensity weight, construct the propensity weight that is the robust to outliers in Y. That seems to be our, it's not trivial problem. And our contribution is that by utilizing the equivalence of the, this construction, you can basically first try develop the outlier robust imputation and then try translate into the final propensity weight. So this is actually our proposal, right? This is our proposal where the final weight contains outlier control in end of the day. So that is our proposal.
I see. So the final estimator is still inverse propensity.
Right.
So IPW estimator. Just
Yes.
You have additional weight for the outlier part.
Exactly. Yes.
I see. Yeah, I was thinking about if you go to the previous slides, I was thinking about to use so you estimate. Sorry, next slide. So equation 17, you use a covariant balancing to get some weight. So essentially here you need to use 1/pi minus 1, right? So you use covariant balancing to obtain some weight, and use that weight here and run the outcome regression using the gamma divergence, and then directly use the regression estimator, imputation estimator. So those two are not equivalent, right?
I'm sorry.
So I mean, so equation 17 is like outcome regression part, right? So if we use like a covariant balancing weight here as 1/pi minus 1, so that part can be like from covariant balancing weight. And then use that weight to run the gamma divergence regression, and then use the regression coefficient to do the imputation estimator. So this estimator is not kind of equivalent to your estimator.
So actually, so what I tried to deliver was that how do you, so this one is algebraic equivalence, and then how do you interpret this one, 16, right? 16. 16 is nothing but the solution of 17. right?
Right.
So 16 is nothing but the solution of 17. So that, oh, I'm sorry, okay. Yeah, 17. So then the emphasis is actually really in 15.
Right.
And yeah, so basically how you make change it, but different imputation. But here you already have a double robustness here, because basically we already constructed we started a doubly robust propensity weight already here in the left side, and then all I did was just translate it, reframe it as an imputation. So this imputation is also doubly robust because the propensity score weight is already doubly robust.
Okay. Yeah, thanks, Jay. So due to time, so I will move to the next talk, but I will talk with you more about. Yeah, thanks, Jay. Yeah.